In this video, let's take a look at the solution of this integral differential equation that has both a derivative and also a convolution integral. To get started, we notice that this is a convolution integral of two functions, the function f and also the function e to the minus 2t. So remember that the convolution integral looks like integral from 0 to t. So if I have f star of g of t, that's integral from 0 to t of f of t minus u times g of u du. So my function f is the function f. The function g is going to be e to the minus 2u. So g of t equals e to the minus 2t. And so the Laplace transform of this function is 1 over s plus 2. And so therefore, when I take the Laplace transform of this equation, I get s times f of s minus f of 0 equals the Laplace transform of cosine of 3t, s over s squared plus 9, minus the Laplace transform of this convolution integral is the product of the two Laplace transforms. The Laplace transform of f is f of s, and the Laplace transform of e to the minus 2t is 1 over g s plus 2. And so I have an equation to solve for f of s. Now, unlike a lot of the problems we've seen in this category, f of s appears on both sides, so I have to get all the f of s's on one side. On the other side, bring the f of 0 over, I get 1 plus s over s squared plus 9. Okay, let's get a common denominator here, so I have over s plus 2, multiplied by s plus 2, I get s squared plus 2s plus 1, f of s equals 1 plus s over s squared plus 9. So f of s is equal to s plus 2 over s squared plus 2s plus 1 plus s times s plus 2 over s plus 1 squared times s squared plus 9, because s squared plus 2s plus 1 is s plus 1 quantity squared. Now I can do a little bit better than this. Let me write this as s plus 1 over s plus 1 quantity squared plus 1 over s plus 1 quantity squared plus this other thing and then when I simplify this fraction, I found the partial fraction decomposition for the first one. So 1 over s plus 1 plus 1 over s plus 1 squared plus this other thing that I have to worry about next. So a couple of comments. I could have set this equal to a over s plus 1 plus b over s plus 1 squared, then solve for a and b. In this case, it was easiest to just use algebra to simplify the fraction. Second comment is that I could have gotten one big fraction and then found the partial fraction decomposition of the big fraction. However, it's usually easiest to divide and conquer as opposed to combine. So I'm going to do this one separately, then I'll do this one separately. Okay, so now we got some work to do. We have to find the partial fraction decomposition for this fraction. So let me flip the page over. S squared plus 2s over s plus 1 quantity squared times s squared plus 9. This will break up a over s plus 1 plus b over s plus 1 squared plus cs plus d over s squared plus 9. If I get a multiply out the denominator, s squared plus 2s is equal to a times s plus 1 s squared plus 9 plus b times s squared plus 9 plus cs plus d times s plus 1 squared. Okay, so let's multiply out the right-hand side. Actually, before I do that, let me square this out here. A times s plus 1, s squared plus 9, plus b times s squared plus 9, plus cs plus d times s squared plus 2s plus 1. So multiplying out, we get as cubed plus as squared plus 9as plus 9a. That's the first bit. Second bit, we have plus bs squared plus 9b. Multiplying this out, we get plus cs cubed plus 2cs squared plus cs. Then multiplying by d, we get plus ds squared plus 2ds plus d. And so matching coefficients, we find that a plus c, well, there's no s cubed over here, so a plus c is going to be equal to 0. Add these up, we get a plus b plus 2c plus d is equal to the 1s squared that I see here. 9a plus c plus 2d is equal to 2. And finally the constant, 9a plus 9b plus d is equal to 0. And so it looks like I have a system of 4 equations and 4 unknowns. Well, I do have a system of 4 equations and 4 unknowns, but I can save myself a little bit of work if I come back up here. I can plug in a number into this to make my life just a little bit easier. So let's plug in s equals -1 into this equation. If I plug in s equals -1, then this goes away and this goes away. So when I plug in -1, I get 1 minus 2 for -1 equals, that's 0, that's 0. This becomes 1 plus 9, 10b. And so b is equal to -1/10. So I can use this down here at the bottom of the page for the system, that b is equal to -1/10. So if b is equal to -1/10, I can bring that over here. So I get a plus c equals 0. A plus 2c plus d is equal to, if I bring the -1/10 over here, I get 11/10. Third equation stays the same. And the last equation, if b is equal to -1/10, if I bring that over, I get 9a plus d. This should have been 2d here, I apologize. 9a plus d is equal to 9/10. And so I've got this system of equations to solve for a and b. Now, unfortunately, there's no real shortcut to this except doing what we can. So let's take, let's see, where should we start with this? Let's start with this equation here. We have that a plus c equals 0, and so therefore a is equal to -c. And so if I take and plug, and also we have from this last equation that d is equal to 9/10 minus 9a. So I've got this and this. The two things that I've circled, I'll plug into the second equation. So we have a plus 2 times c plus d is equal to 11/10. Okay, so we have -10a is equal to 2/10, or 1/5. And so that makes a equal to -1/50. So then coming back here, that makes c equal to +1/50. And plugging into here, we get that d is equal to 9/10 minus 9 times -1/50. So that's equal to 45, multiplying 9 times 5, plus 9 over 50, for 54 over 50, which is 27 over 25. Okay, so we get this fairly, well, not fairly, really complicated mess for these for the constants. And so coming back up here, we found that a was equal to negative 1/50th. We found that b was equal to negative 1/10th. C was equal to positive 1/50th. And D was equal to 27/25. Okay, so with that, let's put that down on the previous page. We have equals 1 over s plus 1 over s plus 1 squared plus negative 1 over 50 over s plus 1 plus negative 1 over 10 over s plus 1 quantity squared plus 1/50th s plus 27/25 over s squared plus 9. Okay, now before I do the inverse transform, let's combine fractions. So if I combine these two fractions, I get 49/50 over s plus 1. Combining these two fractions, I get plus 9/10 over s plus 1 squared plus, all right, so let's think about what we're going to have to do for these fractions over here. We have 1/50th times s over s squared plus 9, and I can run the inverse Laplace transform of this. For the constant, I want to have really 3 over s squared plus 9 to run the inverse Laplace transform, and that means I have to have 9/25 in front to compensate. So 9 times 3 is 27, and 25 I see here. So that is the Laplace transform f of s, and therefore the original function f of t will be equal to 49/50ths e to the minus t. On this part, I have plus 9/10 t e to the minus t. The inverse Laplace transform of this term is 1/50th cosine 3t. And then for this last term, we have 9/25ths sine 3t. And so that is the solution of this integral differential equation.